Okay, so here we're going to talk about how to find damping coefficient when you have the time domain plot of the displacement. So this method works for underdamped system only. And let's recall that the analytical expression for this underdamped response is something like this. It has a sinusoidal function describing the oscillation. It also has a exponentially decaying amplitude, which indicates this envelope. All right. So the idea is, so whenever you want to find damping coefficient from a time domain plot, what you can do is you first find the location of all the peaks, and then you find the value of these peaks. Let's say the value amplitude for the value peak 1 is A1, this value is A2, and then this value is A3, and whatever behind. So AN means the peak value of nth peak, or the value of nth peak. Okay, and then once you got these peak values, what you do is you first calculate a ratio data, and your data is 1 over n minus 1 times log AN A1 over AN. Okay, so that's how you got your small data, and then your damping ratio I should make it clear. That's a data. Zeta equals to data divided by 4 pi square plus data square. So that's the equation we used to describe the damping coefficient. So you may be wondering why we can get these equations. So I'm going to give you a brief explanation. So let's go back to the time domain plot. So the position of each peak, let's name it as T1, T2, and T3. Okay? So let's see. The peak ratio, A1 over AN, equals to AE minus zeta. We just plug in the xt back into this equation. T1 sine omega d T1 plus 5 divided by A E minus zeta omega n Tn sine omega d Tn plus 5. All right. So you can mathematically prove that your Tn is just m minus 1 times t plus t1. Your t is the period of the sinusoidal function. You can mathematically prove that, and I'm going to provide you a live script code on Blackboard showing how we prove these relationship. So once you have these, you can say that, okay, your Tn, let's underline the sinusoidal function. That means these two should have the same value. And then your amplitude A can be cancelled out. So if you plug this back in, then you would have A1 over AN equals to exponential minus zeta omega n minus 1 times t. And because the minus is actually gone, it's actually positive. And then you can take log function on both sides. Then you can take the coefficient from the top, and you have log A1, A2 equal to zeta omega n, n minus 1, and your t is just 2 pi omega d, right? And then remember that your omega d is omega n times 1 minus zeta squared. And then you're going to have n minus 1 times zeta 2 pi over 1 square root 1 over zeta squared. And then you can move things around and solve for your zeta equals to theta 4 pi squared plus theta squared. So that's how we get the equation above. So in your exam, you just need to remember how to use this equation.